Morning, good afternoon, good evening. Information technologies made a considerable leap during past 4 decades, from large supercomputers to the power of parallel computations, from DARPA project to the global internet to virtualization of network and server hardware to AI proliferating to each sphere of modern technological activity. In this video series, I'm going to talk about network technologies that are used in modern networks. I will start with foundations of networks and will proceed to the newest solutions one can see in networking these days. I will be explaining the theory behind network protocols and will use a virtual lab to show how to configure protocols and features on the virtual devices of different vendors. I will start primarily with Cisco devices and will be adding devices of other vendors along the journey. In each video, there will be a theoretical part explaining the operation of a network protocol feature or device operation and a virtual lab where I'll be showing configuration and troubleshooting of network issues. As this video is the first one in this series, let's consider the layer 2 devices. So in modern terminology, layer 2 device are called switches. There was also a term bridge describing the same type of devices, but this term is deemed obsolete, and I will be using these two terms interchangeably. Layer 2 switch is the first device that user traffic encounters on its path toward destinations like servers, printers, or any other application services endpoints. Layer 2 switch operates at the second layer of the open system interconnect model, the data link layer. Its main purpose is to ensure the directed forwarding of user Ethernet frames, where the term directed means that the switch must forward the frame only to the segments that contain the intended recipients. This is not always possible though. Well, to forward user Ethernet frames, layer 2 switches use MAC address tables, which contain mappings between destination MAC addresses and local outgoing ports, behind which those MAC addresses are seen. They do this by learning source MAC addresses of each incoming Ethernet frame. By default, each layer 2 switch implements a single broadcast domain, where the definition of the broadcast domain is as follows. Broadcast domain is a set of devices such that if any one of these devices sends out broadcast frame, this frame is received or heard by all other devices in the same set. Let's consider this simple diagram, which contains three layer 2 switches and three personal computers connected to corresponding switch ports. Right after power on and the load of operating system, all switches have empty MAC address tables. Let's suppose that PCA sends out some broadcast frame. That is the frame with the destination MAC address set to all ones. FF, 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 FF. This could be, for example, ARP request, as in this diagram. The ARP request is sourced from the PCA MAC address, and the body of our ARP request is asking about MAC address that corresponds to the target IP address 192.168.0.23. When such frame is received by the switch at the upper left corner, the switch learns the source MAC address of the frame and associates it to the port number 1. Then this Ethernet switch must forward this broadcast Ethernet frame out all other active ports, in this case number 2 and number 3, because this is the function of Ethernet switches. They must forward broadcast frames in a broadcast fashion. Okay. So this broadcast frame is received by the upper right switch and the bottom switch, and they also learn the source MAC address of the computer A and associate this MAC address to their corresponding ports. In this case, port number 1 on all switches. Then upper right switch forwards the broadcast frame towards personal computer B. Uh, Notice how bottom switch also forwards the frame towards personal computer C, although the body of ARP request is not asking about MAC address of computer C. So this is the flaw of such communication, broadcast communication. It loads every segment. Okay, so personal computer B as well as personal computer C, they must analyze the ARP request. Personal computer C understands that this ARP request is about some different IP address, not equal to its local IP 192.168.0.24. So it just keeps silent. But computer B understands that the ARP request is about its own MAC address because the target IP field has the value equal to its local IP address, 192.168.0.23. So personal computer B generates ARP response, where in the ARP response body, it writes its own MAC address. Also, ARP response is encapsulated to the Ethernet frame with the source MAC address equal to the local MAC address of personal computer B and the destination MAC address of personal computer A. It then forwards this frame or sends out this frame into the network. As upper right switch receives this frame, it learns its source MAC address and associates the MAC address with the port number 2. It then forwards the frame in a unidirectional way because the destination MAC address is known from the local MAC address table of the upper right switch. When upper left switch receives this frame, it also learns the source MAC address of personal computer B, and it also forwards the frame in a unidirectional way. So this is the directivity feature of forwarding of Ethernet frames, as it's stated in the standard. Okay, modern networks should follow the hierarchical architecture where there are 3 layers of aggregation. The first one is the access layer. It aggregates user connections. The second layer is distribution layer, which aggregates access layer connections, connections from all access layer switches. And the core layer is the central part of any campus LAN. It forwards the traffic between different large parts of campus local area network. Um, there are strictly defined functions of each layer. For access layer, it provides endpoints and users with direct access to the network. The distribution layer must aggregate access layers and provide connectivity to services. One of the functions of distribution layer is filtering user traffic because not always traffic from any users must reach any destinations. For example, engineering team must not have access to the financial servers and documents, right? Core layer provides connectivity between distribution layers for large LAN environments and serves as the most performant part of the network. It must not implement any filtering mechanisms or classification mechanisms if we are talking about quality of service in IP networks. So its primary function is high performance forwarding. There is a term availability of network services. The availability coefficient is calculated as 1 minus time of service interruption over the period of monitoring. Usually, capital T equals to 1 year, for example, or 1 month. And the typical value of this coefficient is 5 nines after the decimal dot. This corresponds to 15 minutes of service interruption per year. And this high availability coefficient can only be achieved if you implement redundancy in your network, you tune protocol timers so that your protocols recalculate alternative routes or paths as quick as possible. You implement constant management process improvement in your organization, and also your engineering staff is constantly developing its skills and knowledge. Let's talk about redundancy now. Uh, the types of redundancy that can be classified are as follows. First is device redundancy. Well, device redundancy is when your end system or host personal computer or even access switch is connected redundantly to two different upper layer devices. For example, here you can see two distribution switches that implement device redundancy toward or for access layer switches. There's also hardware redundancy. It's when a route processor and switching engine have two copies, two hardware copies. One is active, one is standby. This way, you can use, for example, or implement in-service software upgrades without turning or powering off your device. You just download your software into the standby route processor and then perform switch between route processors so that former standby route processor becomes active one. And then you download your newer software to the former active route processor. There's also connectivity redundancy. You can see here between two devices, you have two parallel connections. Of course, number of connections can be increased, but not so that the diagram is not clogged. I just used two parallel connections. There's also path connectivity. It's when you use two or more equal cost paths through your network. As we will see later, when we will be talking about spanning tree protocol, it implements uh, it allows for physical redundancy of connections and devices, but it doesn't allow path redundancy. It always blocks one or multiple connections between switches to leave only one active path between any two endpoints connected to your network. And last but not least is power supply redundancy. Of course, if you supply your devices with only one power line, in case of power interruption, you will be facing, well, uh, the network interruption, right? Because in this case, your networking devices will be powered off immediately. Let's talk about path redundancy and how it affects layer 2 forwarding. Well, without this special mechanism, which I mentioned in the previous slide, specifically spanning tree protocol, there are three negative consequences of layer 2 redundancy, path redundancy in your network. First one is, of course, broadcast storm. Suppose one switch, as in this diagram, the upper left switch, receives some broadcast frame. According to the rules of operation of Ethernet switch, it must forward it out of all other active connections or ports, except the one the switch, the Ethernet frame, sorry, was received on. Which means that the upper left switch forwards this broadcast frame towards bottom switch and upper right switch. These switches do the same thing. So the broadcast frame starts looping inside this layer 2 loop, and it's looping indefinitely. And as new broadcast frames are received by any of these three switches, these frames are accumulated in this layer 2 loop, making this segment of network or this part of network unusable and raising the CPU load up to the ceiling, to the 100% of CPU load. The second negative consequence of layer 2 loops is instability of MAC address tables, because each switch must learn source MAC address, and the broadcast frame or frames have, of course, unicast source MAC addresses, always. They do always. And these broadcast frames are looping in both directions, sorry, clockwise and counterclockwise. Each switch sees source MAC address alternatively behind its ports that connect to this loop. So this is instability of MAC address tables or MAC address table flapping. And the last but not the least consequence is receiving multiple copies of frames, because these broadcast frames must be sent out towards access ports. They are constantly copied towards access ports from this loop. So what we can do with this? Of course, we can follow the description of spanning tree protocol and algorithm, first developed by Radia Perelman. And here is her short poem that describes the operation of the spanning tree protocol. So, spanning tree protocol is required to block redundant switched paths. Yes, we add physical redundancy of physical paths, but then we cut off some redundant paths programmatically so that any 2 points connected to your switched network are connected with only a single single active path. Spanning tree protocol ensures that every LAN is connected to every other LAN. It reacts to loss of connectivity by unblocking previously blocked ports. But spanning tree also operates in the reverse direction. If you add new connections, it blocks some redundant paths according to internal calculations in each switch. Spanning tree protocol ensures unambiguous connectivity between any two connected segments. How do switches do this? Well, according to spanning tree protocol, they must collectively elect a root bridge. Root bridge plays a role of a reference point in the broadcast domain. Root bridge has all enabled ports in designated status for each connected segment. So every enabled port on the root bridge remains enabled and not blocked. Root bridge is elected collectively. So basically, each switch considers itself a root bridge at the start of elections, or as soon as the switch or switches are powered on. And when the root bridge is elected, the root bridge sustains current topology by constantly sending out the so-called BPDU frames, Bridge Protocol Data Unit frames, or frames of spanning tree protocol. Root bridge election is based on the so-called system MAC address. System MAC address is kind of base MAC address that is associated with the device itself, with the switch itself. Different vendors choose system MAC address differently. For example, Cisco assigns a separate MAC address or base MAC address to the layer 2 switch. And then the numerically next MAC address is assigned or burnt in on the first physical interface on the local switch. Other vendors choose the MAC address of the first physical interface to be the system MAC address. Okay, so the lowest value of the system MAC address wins elections. So as all the switches initially exchange BPDUs, they tell each other what is their system MAC address, and they hear the system MAC address of their neighbors and the switches behind those neighbors. And finally, only the switch that has absolutely minimum MAC address, system MAC address, continues generating and sending out its own BPDU frames. BPDUs are sent out each 2 seconds by default. This is a standard default timer. Okay, when the root bridge is selected, and here the root bridge is the upper left because it has numerically lowest value. Other switches stop sending out their BPDUs and they start relaying information from the BPDU of the root switch. Uh, by relaying, I mean not forwarding, of course, because these are not user frames. Actually, for example, when upper right switch receives BPDU frame from the root bridge, it terminates this frame. Then it extracts the body of the Ethernet frame. Uh, it has BPDU data, analyze them, calculate new values. For example, there is a parameter root path cost, which must be changed as the BPDU data is propagated throughout the layer 2 domain. And then after all the values in BPDU or in spanning tree protocol are calculated, they are compiled in a new BPDU that is encapsulated in a new Ethernet frame that is sent out towards other or through other active ports. As you can see here, this is the process for upper right switch that also sends out this BPDU data out access port. Each non-root switch must elect a root port. Root port has least cost path towards the root bridge. Here it is obvious because root bridge sends out the so-called root path cost parameter equals 0 because from the root bridge towards itself, the distance is 0. Okay, so both ports denoted as the root port here on upper right switch and bottom switch become root ports. For non-root ports like these two between switch bottom and the upper right, there must be elected a designated bridge. Designated bridge moves its corresponding port to designated port role for the connected segment. Here you can see that, for example, if uh, these interfaces have the same speed, then root path cost will be the same. The root path cost advertised by both switches into this segment. So the parameter bridge ID in this case will break the tie. Bridge ID of the neighboring switch, not the root bridge, because root ID is a separate parameter in the BPDU frame. Okay, so numerically lowest value of root path cost, or in case RPC are equal, the bridge ID of neighbor wins election. And all non-designated ports are blocked. So this is the final steady state of our simple network containing these three switches. Only one interface is blocked because it remains non-designated. There are designated ports, root ports on non-root switches, and only designated ports on the root bridge because the root bridge is a central point in network, and it is also a reference point. There is a notion of spanning tree priority vector. It's an ordered set of values in descending order. The first one and the most priority parameter has having the highest priority is root ID. Then comes root path cost, then bridge ID of the neighboring switch, and then port ID of the neighboring switch. The parameters in spanning tree priority vector are compared bitwise, starting from the root ID until numerically lower bit is found between two compared values from neighboring switch and our local information. Comparison is stopped at this point, and the better candidate is immediately chosen. By candidate, I mean root bridge or root port or designated port, right? In all these cases, there is a comparison between different parameters of BPDU, spanning tree priority vector specifically. There are two flavors of spanning tree priority vector. STP message priority vector, which is sent out in each BPDU frame. It's basically the contents of BPDU, apart from other parameters. And the spanning tree message priority vector contains values calculated by the local switch except the root ID, because root ID is set by the root switch or root bridge. And there is also STP port priority vector. It is stored for each switch port, so it's stored locally, and is compared to the values received in each STP message priority vector. So these two STP priority vectors are just compared. If STP port priority vector happens to be inferior to the STP message priority vector, it is replaced with the values read from STP message priority vector, read from the wire. Okay, and then maybe recalculation of STP topology begins. Contrary, if STP port priority vector is superior to the STP message priority vector, then local switch generates a BPDU frame with its own port priority vector encapsulated into BPDU frame, and local switch sends out this message priority vector with values copied from the port priority vector towards its neighbor that sent out the inferior message priority vector. This is the BPDU frame format. Apart other fields, you can see STP priority vector, root ID, root path cost, bridge ID, port ID. Other important parameters are protocol ID and version. There are many different flavors of spanning tree, like classical legacy spanning tree, rapid spanning tree, multiple spanning tree, per VLAN spanning tree, per VLAN rapid spanning tree, these ones. And also, here you can see message age, max age, which help deleting outdated BPDU information or spanning tree vector priority information from the layer 2 switching domain. Hello time, which by default is 2 seconds, and forward delay timer, which by default is 15 seconds. Forward delay is basically parameter of the legacy spanning tree protocol, which is considered outdated in the modern networks and is not used. There is a faster version of spanning tree, which is rapid spanning tree, and Cisco implements more sophisticated spanning tree flavors like per VLAN spanning tree and per VLAN rapid spanning tree. We will compare those flavors of the spanning tree protocol in later videos. So let's see how STP vector, priority vector, acts in the calculation of spanning tree topology. Here you can see this sample diagram, this sample network, and you can infer which root bridge, which switch is becoming a root bridge, right? I specifically use simple MAC addresses here that happen to denote the host name of the switch. So basically, the switch A becomes the root bridge because its MAC address, system MAC address, is numerically the lowest. then both its local interfaces become designated interfaces or designated ports for the connected segments. Then this switch A sends out its own BPDU frames, continues sending out BPDU frames, and switches B and C are able to choose their root ports. Root ports are the ports that are connected to the root bridge, and the designated ports are the ports towards switch D in this diagram. Well, switch D must calculate which port is going to be the root port and which port must be blocked. If switch D doesn't block any of the two ports, we will have layer 2 loop, right? How does it do it? Okay, here it happens to be the write interface towards switch C that is blocked. Why? Well, because root path cost towards switch D is the same both from switch B as well as from switch C, right? Here I have copied the table from the IEEE 802.1d slash 2004 slash 802.1t subsection. The default STP path costs corresponding to different interface speeds. So you can calculate, right, that switch D receives root path cost equal to 6,000 from both B and C. So RPC is a tie. We have a tie over RPC parameter. Then the bridge ID of the neighboring switch determines the root port and the blocked port, non-designated port. Switch C has numerically higher MAC address than switch B. Based on this, switch D chooses root port towards switch B, and so it blocks the port towards switch C. Okay. Both downlinks on switch D are designated. Why? Because as soon as switch E heard that there is a better candidate for the root bridge role, it has switch A, switch E stopped sending out its own BPDU frames. So for some timeout, switch D didn't see any BPDU frames from switch E. So switch D safely assumes that it can bring up these ports programmatically and assign them as designated ports. But what about switch E? It is connected in parallel with two parallel links towards switch D. And as you can see, if you calculate root path cost, you will be able to see that both directions have the same root path cost. Besides, as switch E is connected to switch D, bridge ID of the neighboring switch is also the same over both links. In this case, port ID of the switch that has sent the BPDU breaks the tie. And so, since 128 is the default priority of each port, spanning tree priority of the port, and port priority also contains the port number, the lesser port number wins elections on the local switch E. So it designates port number 1 as root port and port number 2 as non-designated and block it. So now let's start building our network. I'm using virtual environment based on EVNG, emulated virtual environment next generation. I think this is a very good platform, virtualization platform, to create virtual labs, both networking as well as containerized or server-side uh, architectures, etc. So here you can see the initial part of the network, future network, which I'm going to develop throughout this series. And there are 5 switches at the access layer and 2 switches at the distribution layer. Um, and although these switches have different icons, to be honest, all of them support routing, even in physical, I mean, the real devices at the access layer nowadays support routing as well as the switches at the distribution and the core layer. But now let's suppose that we are configuring only L2 features. And so these distribution layer switches are not going to get any IP configuration or routing configuration. We will configure only layer 2 switches. And in this video, I'm going to show you the basic configuration of Cisco iOS devices. So let's connect to the consoles of these devices. So this is the switch number 1. The first thing that I would like to show is the number of commands that is allowed in the initial mode, initial configuration mode, which is denoted as host name. By default, it is switch and greater than symbol. So as you can see, the list of commands almost fits into one screen. But this is a limited mode of configuration. You are not able to configure anything in this mode. You have to first enable or go to the privileged mode of configuration. Let us check what is the command list that is available here. And we can see that the number of commands is greater than the number of commands available in the ordinary user mode. Now, in order to configure some global parameters that pertain to the device itself, like its host name, we have to go to the conft or configuration terminal. Configure terminal or global configuration mode. By the way, you might have noticed that I used some key to autocomplete the command, and this key is tab. I can hit tab and autocomplete the whole command word, provided I entered enough symbols to unambiguously identify the command. Now let's configure just host name of the switch. For this, we have command. No surprise, it is host name. And then I configure the host name of the switch to be SW1. As you can see, the prompt immediately changes to the new host name, and it shows the current configuration mode. Now, if I reload the switch now, without saving this configuration, it will come up next time with a clear configuration, or in other words, without any configuration. Included host name will be absent. Now I have to write this configuration into non-volatile memory, or into the file that is called startup config. This file will be applied each time the switch or any other device when we will be tackling the routers, firewalls, etc. The startup config is the file from which the device reads its initial configuration when it reboots. So for this task, for the sake of saving the running configuration into startup configuration, there is command copy running config startup config. Now I have to confirm the file name, and here we are. We have startup config. Let's produce it on the screen, and yeah, startup config contains this hostname command. Other options are set to their defaults, including configuration of all interfaces. As you can see, the configuration is empty, which means there are default parameters for these interfaces. I believe show running config all will show the all default parameters. You see, the running config in this case is much more larger, bigger, but these configuration parameters are default parameters, having default values, including Ethernet interfaces and their configuration, etc. So let's configure now host names for the rest of the switches. This is the switch 2. Enable conft host name switch 2 and save. By the way, I can use WR command, which is much more faster, uh, much faster than the copy run start. But they say that this command is deprecated in newer versions of Cisco iOS software. And for sure, as I know, this command is not in among the options in such Cisco software as NXOS, for example. Now, let's continue. Switch 3, enable, configuration terminal, host name, switch 3, Control Z, and WR. Switch 4, and switch 5. Switch 6, the distribution switch. And the last one, switch 7. Okay, and save. Now, let us check the MAC address tables of these switches. For this, we have command show MAC address table. As you can see, MAC address tables of the switches are not empty at the moment because these switches have learned the source MAC addresses of their neighboring switches. Okay, so switches send each other some special frames of network management protocols like Cisco Discovery Protocol, Dynamic Trunking Protocol. We will be discussing these protocols in the future videos, but for now, let us check also the, oops, I have already console of switch 2 open. Um, for now, let us check the status of interfaces. For this, we have command show int status. As you can see, this is a concise output of the status of the interfaces on the local switch, as well as which VLAN it is assigned to. By default, all, all Cisco switches have only one VLAN, VLAN number 1. And this VLAN is a factory VLAN. You cannot delete this VLAN from the configuration of a Cisco switch because this VLAN is also used for those network management protocols, special protocols that are needed for the network itself to operate properly. Okay, we can see that on this access layer switch, only 2 interfaces are in status connected and up, physically up, and line protocol is up on them. Let's check it. Show interfaces, Ethernet 00. Yeah, we can see Ethernet, that is physical interface, is up. Line protocol, it has Ethernet protocol is also up. The interface is connected. The hardware Ethernet address is this one. We can change, by the way, MAC address assigned to the interface. This is a burnt-in address. So this address actually, like, permanent address of the interface. It never it never lost. Well, until maybe you replace the Ethernet module with Ethernet ports. Okay. Now, let us check. I mentioned CDP protocol. CDP, or Cisco Discovery Protocol, is the protocol that allows switches to learn their neighbors, their capabilities, and what interfaces are used on the remote side to connect from the connected device to the local switch. The command looks like show CDP neighbors. Show CDP neighbors. We can see that for this access layer switch, there are only two neighbors. And indeed, based on this topology, switch 1 has only two connections, two uplinks toward the distribution layer switches, switch 6 and switch 7. And indeed, the device ID contains the host names of those switches that we have configured previously. There is also command show CDP entry, and you have to put the device ID here to get more detailed information about specific neighbor. I believe you can omit this. Oh, yes, you cannot. So please notice that among the capabilities of the switches are shown router, switch, and IGMP. Okay, but this is the distribution layer switch. Let's check on the distribution layer switch. What show CDP neighbors command tell us about switch 1 capabilities? Okay, show CDP neighbors, or just entry and switch 1. Okay, despite the fact that switch 1 uses the Linux 2 Advanced Enterprise K9-M iOS image, it is marked with capability router. So basically, even this image contains routing functionality or capabilities. Other capabilities are, of course, switch, because switch 1 can forward Ethernet frames, learn MAC addresses, execute STP protocol, right? And IGMP protocol as well, Internet Group Management Protocol. We see here hold time for this entry, 149 seconds. Each CDP message is sent out by each Cisco device once per 60 seconds. So basically, if we refresh the output of show CDP neighbors periodically, we would see that the maximum value of the hold time is 180 seconds, and then it is counted down toward 120, right? Which one is the closest one? It's switch 2, right? Switch 2. Okay, you can see here 179. Here it has 130. So basically, it's even a bit less than 60 seconds. But by default, it is 60 seconds, and we can check it with the show CDP command. Sending CDP packets every 60 seconds, and hold time is 180 seconds. So basically, it is a not strict parameter, not strict value, I mean. Now, let us check the frames, how they look like in the Wireshark utility. We can perform packet capture. And let us capture the traffic on interface Ethernet 0/0 of switch 6. EVNG is going to launch the Guacamole console, where there will be Wireshark utility. as you can see, and it immediately starts capturing packets on the connection between switch 1 and switch 6. And the first packet, the first frame received on the Ethernet 0/0 on the switch 6 is spanning tree protocol frame or BPDU frame. Let us check the spanning tree information inside this protocol, inside this frame. So this is a BPDU type configuration. It is by means of the configuration type of BPDUs that Cisco switches sustain stable topology, because root bridge is sending out BPDU frames of type configuration each 2 seconds. You can see here 31 seconds, and let me stop scrolling. So 33 seconds, 35, 38, etc. So roughly 2 seconds is the hello timer of sending out a BPDU frame. Now, some BPDU flags, topology change, there is no topology change, so nothing to acknowledge and nothing to advertise. Root identifier. This is the bridge that identifies itself as the root, and all other bridges or switches do not consider themselves as the root bridge. Let's check on switch 6 what or where is the root bridge located, or maybe switch 6 has become the root bridge. Show spanning tree. Now you can see that the root ID is having priority 32,769 and address AABBCC 0010, I mean 0100. Well, and we can see root port, and that is not possible, but this must not be the case in production network. But currently we have the root bridge on the access layer. Actually, switch 1 is the root bridge for the broadcast domain based on VLAN 1. Let's check here. Show spanning tree. And indeed, this switch considers itself as the root bridge. This bridge is the root. You can see here the message. And also the address, the system MAC address of the device is the same as the one we can see here on switch 6, right? So this is not correct. This is incorrect totally, I mean. In your network, it is distribution switches that must be, one of them must be the root bridge for the broadcast domain. How do we correct this situation? Well, remember, we have priority field for the root ID. We can lower priority for the intended root bridge, and then re-election will occur immediately after we change this priority. So let's do it. For the purpose of changing priority of the switch, in order for the switch to become the root bridge, we have command spanning tree priority. Spanning tree, well, VLAN. Then we have to specify the VLAN number. Currently, we have only one VLAN. And let's just manually set priority to 0. This is absolute minimum of the priority. Now, let's check here the spanning tree. See, now the root ID contains AABBCC000B00, which is the root bridge seen through the port Ethernet 0/0. So basically, switch 6 indeed has become the root bridge for this whole domain. But what if this switch goes out of order? Then again, switch 1 will be elected, right? Because it has just the numerically lowest system MAC address. So let's configure switch 7 as the backup root bridge. How do we do this? Okay, we issue command spanning tree, right? I mean, VLAN 1 priority. And now, uh, because these are Cisco switches, they implement per VLAN spanning tree plus. And so we have to use this value. The next value after the 0. I will explain these flavors of spanning tree in later videos. For now, it's just a configuration of basic parameters. So, who is the root bridge here? Show spanning tree. Okay, you can see that first, IEEE is the legacy spanning tree protocol that uses the forward delay timer, which by default is 15 seconds, as you can see here. Max age timer is by default set to 20 seconds, and hello timer is set to 2 seconds. The root port on this switch is port number 6 or Ethernet 1/1. 6 is the its numerical value, and Ethernet 1/1 is its position on the so-called virtual models. Okay, so this is, I believe, it for the first video. We have covered here both theory as well as initial configuration. We configured host names of the devices. We checked their MAC address tables. This command, by the way, is available also in the ordinary user configuration mode. So in the next video, I will continue discussing spanning tree protocols, and I will be developing this virtual network. So stay tuned, and thank you very much for your attention. Bye-bye.